I'll give you an overview today on the semiconductor, what a semiconductor is and what the field's all about a little bit. But what you're really going to hear over the course of this semester is people from industry coming in and telling you about, more formal versions of these career stories, but more importantly, what their company does, what the industry is about. One of the things you'll see is there's a number of different segments within the semiconductor industry. We say it's an industry, but there's different segments within that. There's an ecosystem between all the different kinds of companies in the semiconductor system. So whether you're in, we tend to think, if I say what discipline should you major in here? What should your major be if you want to work in the semiconductor industry? What major do you think you need to have to get into the industry?
Probably like materials, electrical, computer, or like maintenance, right?
Could be, could be. Anybody else have any thoughts? Yeah.
Like you can do mechanical, chemical, computer, electrical.
Mechanical, yeah, chemical, mechanical, computer, chemical, or electrical?
Maybe industrial or some kind of other management combined with engineering.
Industrial or management, yeah. Supply chain, wherever that exists nowadays, industrial engineering, school of business, whatever it is. Good. A lot of it's international, by the way. If you look at where chips and boards are made, the chip may be made in South Korea, the board may be designed in Taiwan, it may be assembled in the US, put into a system sold in Europe. So the industry is quite international also. So I'm a professor in ECE, but one of the things that we're trying to do, is my role in the semiconductor degree program, is to get more engagement in some of the disciplines outside of ECE, because industry comes to us and say they want people in all these other disciplines. How do we build that expertise?
I think you went backwards.
Oh, I went backwards? That's not my slide? Okay. I thought it looked a little weird. So I'm going to give a talk that's derived from something that Professor Lundtrom has given the past few years, but I'm sort of taking over this role. And really, many of you have probably heard of the CHIPS and Science Act. This is President Biden signing it into law. This was something that had actually been in the works for a while, but actually got formalized in 2022. And it's really aimed at it's a kind of a once-in-a-generation investment in the nation's future to look at these technologies being important. One of the reasons people realized this was so important is during the pandemic, you couldn't buy a car. You couldn't buy electronics. There were a lot of things that the supply chain had broken down. Anybody's family tried to buy a car in 2021 or anything? Okay, I bought a car in 2021. We went to the dealer and said, well, normally it's like 5 trim levels. We're only making 1 because we only get enough chips. We only get enough semiconductors to put together 1 trim level. Here it is. We normally would have 20 cars on the lot. We got 1 out there. If you want it or don't you want it? Really short negotiations, right? So it became apparent that the supply chain was really impacted by the pandemic, but more in general by any kind of fluctuation. So really the CHIPS Act is intended to reshore or bring back into the US semiconductor manufacturing and make our supply chains more resilient to these kinds of things. It was intended to bolster strength in chip design and manufacturing tools, and really to regain some edges in competitive technologies that the US had kind of lost. If you read just the statistics on where the most semiconductor chips are made in the world, which country leads that right now? Taiwan. TSMC is the largest producer by number of chips, but not necessarily by impact in the industry, and they don't cover everything. Global Foundries will tell you a lot of things they do. You'll learn some of that tonight, I think, at the lecture. It was really intended to also accelerate the pace of innovation. This has always been an industry that spends a lot of money on R&D. Innovation is a huge part of the industry, and we'll talk today a little bit about why. But this has been an industry compared to all others that's always pumped an awful lot of money back into R&D as they go forward. So we want to first talk about semiconductor electronics as kind of a foundational technology. So most of you are probably carrying around quite a bit of electronics. Almost everybody most likely has a phone of some sort. You may have a laptop or a tablet. What else do you have that's probably electronics? Anybody carrying anything unusual? Oh, everybody's pointing to their wrists. Either everybody's wrist just suddenly started hurting or you're carrying electronics on your wrist. Good, okay, that's good. There's a lot of personal medical devices and stuff. But the first question we have to answer is, what is a semiconductor? Right? So you're all probably familiar with these kinds of materials around the screen right now. We have metals, conductors, which carry electricity. So if we plug into the wall socket, the electricity that's coming to us is flowing through probably copper wires. They're good electrical conductors. We use them because that allows the electricity to flow freely. On the other end, we have insulators, glass being an interesting one. Silicon dioxide is actually an insulator used in the industry. And that's what we wrap the wires with so we don't get electrocuted. You can plug your plug into the wall outlet and not get a shock because we put electrical insulators. So it's block electric current. We've known this for a long time, right? You didn't have to get shocked by the electrical outlet too many times, just like you didn't have to touch the hot stove too many times before you figured out, hey, I probably shouldn't be doing that, right? So we use insulators a lot. So semiconductors fit in between this. We have really good electrical conductors that carry electricity really well. We have insulators that block electricity. And in between, we have semiconductor materials. This happens to be a chunk of silicon, I think. They tend to look kind of glassy. They tend to be opaque, at least most of them we use. But they're really, the magic part is you can change them from being sort of the conductivity of metal, not quite, but pretty good conductors, to being fairly insulating by a number of things. You can actually put chemical impurities into them. You can shine light on them. You can put them in electric fields or apply a potential, which is really what makes transistors work. But the key is you can change the electronic or optical properties by a lot. By like orders of magnitude, you can modulate what these things look like. So if you look up in a textbook what copper is, there's a conductivity of copper. If you look up in a textbook what the insulating properties of silicon dioxide, and there's kind of a number. But for semiconductors, depending on what you do with them and where you put them in a device structure, you can change their properties by a lot, right? This is like almost as much as the temperature difference between like August and January, right? We know the temperature changes by orders of magnitude. At least it felt this morning like it had, right? But yeah, by way more than that. That's a small temperature change, but this is huge, right? So think of it that way. Microelectronics is the design and manufacture of complete electronic systems based on semiconductor chips. So we somehow are going to use those materials we talked about, those semiconductor materials, to actually make chips. And there's a lot of steps in between those two, but that's the idea. The basic building blocks, the atoms, so to speak, of electronic systems are usually transistors. Transistors are basically switches. They can be on or off electrically, just like this thing over here, right? This thing on the wall is a switch. And ever since you were kind of large enough to reach it, you've probably known how to operate that thing and do a basic logic of when the switch is up, the lights are on. When the switch is off, the lights are off. Unless you have like a three-way switch with this entrance and that entrance, and then it's some combination of where this switch is and where that switch is that can turn the lights on and off. So you've known that basic logic since you were large enough to reach the light switch. And then for the next 15 years, your parents told you, shut the damn lights off when you're not in the room, But anyhow, so you've all known that idea of logic, and you knew that logic of how a switch could make, in this case, a light turn on or off. So you already understand a little bit about that logic, right? So it turns out those are transistors with critical dimensions measured in the range of nanometers. Okay, we'll talk a little bit later about what that means, and it's really, really challenging if you see what happens. A leading edge chip may contain 100 billion transistors on the chip, 100 billion on one chip. And you may have something like 60 miles of wires on that chip, all those copper wires interconnected around, just like the wiring that comes to your house. The industry puts that many on every chip. Okay? And each of you probably carries multiple chips, right? If you have a cell phone, you're carrying lots of chips on that cell phone. And we call the industry that does all this collectively the semiconductor industry. So notice that semiconductor on some plane means that material we start with. Semiconductor on some level means the chip that we build. People talk about buying semiconductors. They mean buying those chips. And at some point, it means that whole industry, those segments that include how you design circuits, the design tools used to make circuits, the foundries that maybe fabricate the chips for other companies. Independent device manufacturers tend to be companies that have, or are companies that have both the chip design and the manufacturing all in their company, and usually will sell a branded chip to the world, like Intel inside microprocessors and things like that. Then companies that make the process tools that go into these fabrication plants, and the companies that vend materials that can be used for this whole processing. So all those things are sectors within this broader semiconductor industry. And as I said before, these are all kind of interconnected into this ecosystem. So you talk to people about the semiconductor ecosystem, and they mean all these things that tie together, where you can be at one end. These days, in your garage, you can design a chip, and you need some cash to do this, but you can actually have a foundry build that chip for you, and some other company package that chip for you, so you can get in the game without spending the tens of billions of dollars it takes to set up your own chip fabrication facility. Companies like Global Foundries will gladly, for a modest amount of cash, do that fabrication for you, right? And they have the infrastructure and the design kits and all that to make it work. So where are semiconductors? Well, they're everywhere, right? We already talked about cell phones or laptops, big data centers. TVs are not only embed electronics in them to do the reception and signal processing and display the image, but the screen itself, the LCD screen itself, is also made by a process that's very comparable to what the semiconductor industry uses, right? So there's already kind of that same technology there. We embed it in things like smart thermostats. Your refrigerator almost certainly has electronics in it. Your Alexa, your solar cells, your car. I mean, they're all over the place. Everything we do in terms of how we compute, communicate, connect to the outside world is really very integrated in this whole electronics thing. I mean, it's really everywhere. You've grown up not knowing a world where there weren't electronics like everywhere, right? If you talk to your grandparents, they probably are scratching their head a little bit about smartphones and all this kind of stuff. What's this app? Come over and help me set up this thing. Anybody had to set up something for their grandparents of how to make, wow, look at all those hands going up. Excellent. Okay. This is moving pretty quickly. And that's another take-home message, right? The reason you have to go over and explain this to your grandparents is that every year electronics is better and more powerful and does a lot more than the previous year. So if you think about a generation or 2 generations between your grandparents and you, there's been a lot of evolution, a lot of generations of technology that have come along. Constant change, constant innovation. If you buy this year's cell phone, it's vastly better than last year's cell phone, which is vastly better than the previous year's cell phone in lots of ways, in processor capability and raw speed and amount of memory, putting AI on phones now. So all this is happening because the electronics industry has been so successful at innovation and moving forward. Okay? Oh, I mentioned ChatGPT too, right? So all the challenges of the 21st century, name a challenge of the 21st century, whatever you're interested in socially, energy, environment, health, climate, economic opportunity, national security, electronics is playing a role in monitoring it, predicting it, helping even to maybe to impact it, right? And at the other end, data centers are chewing up, we were talking on the way over about how much electricity data centers are chewing up. So that becomes a challenge all its own. Oh, I mean, it's so successful with the electronics and the whole idea of data centers for Google and Amazon and everything else, that now that's chewing up a huge amount of the power budget in the US. Addressing these challenges will require us to keep doing faster computing, more data, better communications, and it all relates to the core semiconductor technology that makes it work. That's the hardware of what makes this whole industry work, right? We wouldn't have the internet. We wouldn't have the Internet of Things. We wouldn't have ChatGPT and is TikTok still in business or did the government finally put them out of business? We wouldn't have TikTok if it wasn't for the semiconductor industry. That's the platform on which all this works, right? Okay. And any nation that really aims to control its destiny in the future has to be strong in semiconductors. So the US is making a huge strategic investment, but lots of countries around the world are also realizing the same thing and making comparable investments to try to be players in this field. So that's where we are. But let's take a brief look at the history. Where did all this start? So we go through various areas of electronics, and this may actually go back to your great-grandparents' generation, not just your grandparents. But back in the day, we actually started with vacuum tubes, and then in the early days of transistors. So vacuum tube, anybody here have a vacuum tube amplifier? Maybe like a guitar, electric guitar? A few people in the back, electric guitar amps that are vacuum tubes. They're still around, right? Why do you use vacuum tubes for an electronic guitar, right? Why? What, for electric guitar? Is that where you guys use vacuum tubes? Why do you use vacuum tube amps? They sound better? Okay, well, that's subjective. All right, good. Sound? They sound cooler? You got this nice orange glow. That's cool. Okay, but vacuum tubes was what electronics was back in the 1930s, 1940s, even in the 1950s. And it relates to some fundamental effects. Edison, we all know Thomas Edison invented the light bulb, but he was also very instrumental in some of these basic effects. Thomson with cathode rays, Fleming with the diode, De Forest with the triode. The basic idea, this is a vacuum tube. They tend to be big. They tend to be things that are like an inch in diameter and 3 inches long or something. Back in the day, we had television based on vacuum tubes. You could open up the back of the vacuum tube and see, or back of the television, see these big vacuum tubes in there and stuff. They got hot. They glowed orange. But the basic idea is you had a hot filament, like an incandescent light bulb, which is, you probably still remember those. You heated it up, you got electrons actually emitting from it. So it tries to emit emitting light, you were emitting electrons, those streamed from one electrode to the other, and you had another electrode in the middle that would kind of modulate those things. You could do this basic modulation. You had electric current, do those electrons flowing, and you just had some kind of modulation. Well, we had radio. This is, state of the art. Instead of sitting around trolling the internet or looking at TikTok or watching your video on your phone, back in the 1930s and 1940s, people sat around and listened to the radio. This is the radio here, right? And you would gather around and listen to radio programs. Old-time radio, you can still sometimes hear it. This is a television. These are the Beatles in 1963 or something. You had a television. This is black and white, but you also make color television on vacuum tubes. Open up the back of it. Here's the vacuum tubes. This is the picture tube right here, the big picture tube. That was a vacuum tube. And then here are the discrete vacuum tubes in the back of this. You can count on one hand how many tubes were in it. So it wasn't very large-scale electronics. But we went to the moon on vacuum tubes, basically. So, it was a possible thing. We got too much animation on here, I think. This was actually a computer, 1945 computer called ENIAC. It was 17,000 vacuum tubes. It weighed 30 tons and 150 kilowatts. It wasn't exactly a portable electronic device. It certainly wasn't wearable. It used 1,000 square feet of floor space, so think of something at least half the size of this room just for this one computer. And you had to change about 50 vacuum tubes a day. They had full-time people going through and taking out defective vacuum tubes and putting in fresh vacuum tubes. The whole idea of a bug, everybody's heard of a computer bug. That literally was bugs, insects crawling around in the back of this thing and shorting tubes out. That's how we talk about bugs in computer programs. It's because bugs would get into the vacuum tubes, right? This thing did a grand total of 5,000 add and subtract operations per second, right? If somebody tried to sell you a computer today that had 5,000 operations per second, you'd say, I ain't gonna wait around long enough for that to happen, right? Had no hard drive, no storage. The inputs were actually on punched paper cards, right? But that was 1940s computing. It was actually a big deal at the time. Vacuum tubes, right? The transistor was invented at Bell Labs in 1947. Bardeen, Bratton, and Shockley. These are the three people here. By the way, Bardeen won 2 Nobel Prizes. One for this. Anybody know what the second Nobel Prize he won was? Anybody heard of superconductors, superconductivity? There's a BCS theory of superconductivity. He's the B in BCS, so he won 2 Nobel Prizes in that scene. This is the first transistor. This is pretty crude. This is a chunk of germanium with this big point contact. This is like a centimeter scale device, but this was the first real demonstration of a switch, a transistor that could eventually work into a switch. 1947, won him a Nobel Prize in physics. There's various people that have said, this is one of the most important inventions of the 20th century. Clashing egos and top secret research. I'm surprised we don't make movies about this, but anyhow, it's featured in some news articles you can see. But this was a huge thing. We went from those vacuum tubes into transistors, and that allowed us to now start thinking about things like a portable radio. Instead of a radio that was the size of a refrigerator, you could think about a radio you could carry around your hands. This happens to be one that used Texas Instruments, TI transistors, had a grand total of, the original one was 4 transistors in it. But now you could carry around in your hand, right? You didn't have to be sitting around this big box in your living room. You could carry around this portably, ran off a battery, it was portable with you. This is one a few years later by Sony. This is what really got Sony started. It was a little 6 transistors, a little shirt pocket radio. It wasn't quite really small enough, but it would kind of fit in your shirt pocket if you stretched out a little bit. And this thing cost $585 it cost $49.95 in 1954, which is $585 in today's money. That was expensive, right? I don't know if this will play. I don't think I can really play, but this is a video we can put online. You can see the transistors here. These are actually individual transistors on a printed circuit board, and these are somebody's fingers. They're actually assembling this transistor by transistor on a printed circuit board. This was actually done in Indianapolis. There was a company there that produced these things. So that's kind of what electronics looked like in 1950s. It was transistors, but it was still basically that individual component. One transistor at a time, you'd put on a circuit board. It was interesting, there's a nice IEEE Spectrum, IEEE is our professional society in electrical engineering, but there's a nice article on this when they talked about the fact that the original design for this in the prototype stage was 8 transistors, but transistors were so expensive they got it down to 6 transistors, and they eventually got it down to 4 transistors. And it sounded really tinny, the sound was crappy, but it was cheaper. It was cheap enough to actually somebody buy it. And this was an expensive investment, right? So what happened? So if you think about that $585 in 2025, or equivalent money, what could you buy nowadays for $585? They were talking about you were buying 4 transistors back in the day for that amount of money. Today, how many transistors do you think you could buy for $585? Right? I mean, you could buy not the latest iPhone or latest, Galaxy or whatever, but you could buy a reasonable phone for $585. You can certainly buy a laptop. You can certainly buy a TV. But how many transistors do you think you're buying now for the same amount of money? Instead of 4, you're buying tens of billions, right? We said a chip had tens of billions on it. So now if you think about it today, a transistor costs like a microcent. We've gone from $1.50 a transistor to a microcent per transistor in that time. How has this happened? How did we go from so expensive to so cheap? I mean, transistors are so cheap nowadays, you don't even worry about the cost of the transistor, right? It's everything else that's really the cost in there. Right? How did we do that? How did we go in that huge, huge change in cost? Okay. Well, this answer is we did integrated circuits. Instead of taking one transistor at a time and manually placing it someplace, we figured out how to make lots of transistors all at once, kind of a big parallel process. So this, again, Isaac Asimov, science fiction writer. Anybody reading is Asimov still something you read in high school? Science fiction novels and stuff. Isaac Asimov was a fairly famous writer back in the day, and his quote was, "It was the most important moment since mankind emerged as a life form." That's quite a quote, right? I mean, since we crawled out of the primordial muck, this is the most important invention? Well, maybe it is, right? I don't know. Let's talk about it. And what he's really referring to was this planar process, not the transistor per se, but when we took it from individual transistors to a whole manufacturing process, we can make lots of transistors at once. And there's different people who get credit for some aspect of having invented the integrated circuit. But at least the monolithic integrated circuit was really Robert Noyce from Fairchild. Jack Kilby from Texas Instruments developed I think 4-transistor integrated circuit about the same time, but it wasn't really integrated. The interesting part about Kilby was he was like a first-year engineer at Texas Instruments, and the company shut down for 2 weeks every summer. Because he was a brand new engineer, he didn't qualify for paid time off for this shutdown. So he was working in the labs. And while he was working there by himself, he started trying to mess around with putting a few transistors together. And so here's this kind of first-year engineer in industry who developed something that was really the part of this whole revolution since then. So pay attention. Just because you're in your first job doesn't mean you can't do something significant, right? So here's the idea. You took those transistors, and instead of thinking about making one transistor at a time and then wiring them up later, you started making multiple transistors on a chip. So this happens to be a chip. This is a piece of silicon. It's got lithographically defined things on here, printed things on it. You see some wire bonds around the outside to connect to the outside world, and there's a couple of transistors on this. So now you had more than one transistor, and you had a circuit. This is actually a logical NOR circuit. So if you think about logic elements, this is a 2-input NOR gate. This is actually from the Apollo spacecraft, which would have launched in the late 1960s. So this chip must have been designed well before that. But in the late 1950s, Noyce and Kilby sort of independently developed things. But Fairchild was able to push it forward because they had this idea of a monolithic circuit chip. It was made out of silicon, which is an interesting semiconductor. They had a planar process and a surface passivation process. Remember this name, John Atala, because that's an important part of history in this process too. So now you got to the point where instead of having these individual transistors, you now had a package that looks still like a fairly primitive package, but at least that package contained a full logic gate within it instead of just having to wire up individual transistors. So now you're on a pathway. Instead of saying I've got individual transistors and now I have to go build a separate circuit with that, as you manufacture it, you already had the circuit all together. The transistors are already wired together to do circuit function. So this is the first silicon MOSFET, and MOSFET is a transistor, so think of it, forget about all these words up front, it's a transistor, so it's a switch. It's the basic switch element that allows you to do logic, 1, 0, 1, 0, and stuff like that. Metal oxide semiconductor, remember we talked about those 3 materials. We have a metal material, which is electrical conductor. We have an oxide, which is an electrical insulator. And then we have a semiconductor that allows us to do this modulation, to change things from being conductive to non-conductive. That's our switch idea. You make the semiconductor conductive, it's on. You make the semiconductor non-conductive, it's off. Okay? And you can do that with an electrical input. So this happens to be a structure. Here's the silicon, source drain, here's a gate, there's an oxide here, and so I think we have it animated up a little bit, but there's the metal, there's the oxide, there's the semiconductor. That's our MOS in our MOSFET terminology. That becomes a source, gate, and drain. You can control it by putting specific voltages on those 3 electrodes. So now you can electrically turn the switch on and off. So remember our analogy of going to the wall and pushing the switch up and down? Well, you can't hire a bunch of 4-year-olds to run all the elements within your circuit. You need to have a way that one transistor can drive another transistor, can drive another transistor. Now it's all electrical. The input's electrical, the output's electrical. So you can do logic at various scales. You can have logic that flows through from input to output. So everything was wonderful. Remember we mentioned Atala, John Atala. He was a PhD from Purdue in 1949. So there's lots of semiconductor legacy at Purdue. You're in a place of rich tradition and history on all this. This happened to be Bell Labs, but between Bell Labs and Fairchild, this industry kind of got spooled up. By the way, I should mention, the industry had lots of acronyms, but if you can figure out what the acronym means, they're all really pretty informative. Once you understand that this is MOSFET means metal oxide semiconductor, you kind of understand the structure. Once you understand it's a field effect transistor, you kind of understand the operation. So through this whole semester, if you can figure out what the acronym means, you probably have a pretty good idea what the device is about. People aren't very obtuse. They tend to label things based on what it really does. And so just try to decode the acronym and you'll be 90% of the way to understanding what the thing is, right? Okay, great. So now we've got a transistor. We've got a simple idea for an integrated circuit. So how do we really do these things? Well, it all works based on wafers. We don't ever process a single circuit. What you wind up doing is processing lots of circuits together, right? You have this big parallel process where not necessarily all at once, but at least in major blocks, you can kind of process the thing through from beginning to end. So you start with a silicon wafer. These are wafers. They're pieces of silicon. They're fairly thin. They're round. Just to give you a scale, I don't know exactly what these are, but the industry is currently processing either 8-inch or 12-inch wafers, and that would be 200 millimeters or 300 millimeters if you really want to be an insider in the industry. But think about something that's either the size of a salad plate or a dinner plate as kind of the size of the wafers that are most common in kind of the leading edge industry right now. It depends a little bit on the technology. We tend to talk about, the mainline, high production Taiwan silicon stuff is all 12-inch. Global Foundries does a lot of 12-inch. But there's more niche parts in the industry too that are a lot 8-inch and things like that. So there's a different variety of things. So the thing to remember is that these have gotten bigger over the years. This was a much previous generation. They've gotten bigger and bigger and bigger. And so not only do we process a bunch of chips on this wafer, but the wafers themselves get bigger and bigger over time, or at least did until you got to about 12 inches, and then that's been kind of stable. So what really happens? And let me just tell you, this is going to be a cross-sectional view. So I'll take that wafer, and this is just a cross-section. And we're going to look at kind of one device area. But just remember that this is happening, millions of devices that way and millions of devices this way. So it's not, this is just one little transistor in that whole big chip area we're going to make, or the whole big wafer area we're going to make. But we start with a piece of silicon. This is our silicon wafer. It's p-type, which just means it's got chemical impurities of a certain type. It's got a silicon dioxide layer. The yellow is silicon dioxide, which is our insulator. That's all important. And we start with we have a series of steps. So this is a step process recipe or a process run that you'll go through. It's a recipe. You follow step by step by step. And so we first would deposit or grow the silicon dioxide. We would then coat it with a photoresist. We put down a layer of material that's photoactive. Photoresist means it's photoactive and it has some resist properties. It's resistant to a chemical etchant, say, for instance. We put it down. We got a coated wafer. Nothing's really happened yet. The magic happens when we bring a mask. We have a mask layer that's, if you were a few years older, I'd say it's like a photographic negative, but you don't know anything about film photography. Anybody here still use film photography? Okay, a few people are still retro. Good. So it's like film photography. You have a negative you would put down in contact with this, in this case, a coated silicon wafer. You would shine light through it to transfer a pattern, just like we would make a photo pattern of something. We would print there on photo paper, but this is just that same idea. Go ask your grandparents again what film photography was and how they thought about negatives. They would go to Walmart or CVS and have film developed and get back the little negatives along with photo prints. Great topic with your grandparents sometime. They would take a mask, you bring a mask and bring it in close proximity to the surface. You would now expose it. You would have a light source and shine light that would only come down through the holes in the mask or the apertures in the mask. Those regions where you shine light get modified. You now get light that modifies those regions of the resist. Where you had an opaque region, the light got blocked. So you can imagine now you're taking that pattern, whatever pattern you had made on that mask, and you're transferring it somehow into this photoresist. So you now take the mask away, you put it in a chemical that will develop it. So you've now modified some regions of the resist here, and you now can develop them away. So you now open a hole in the photoresist that matches the pattern that was on your mask. So whatever pattern you had on the mask now gets transferred into the wafer. Magic, right? Well, that's half the magic. The other half the magic is now you do something with that photoresist, right? Photoresist is think of it when you put it on, it's like pancake syrup. You bake it out a little bit, it becomes more like plexiglass, but it's still this organic layer on the surface. But what you almost always do then is use that to transfer a pattern into the underlying silicon wafer. In this case, we had this oxide region, so we're going to use it to etch the oxide. We put it into either a wet chemical bath or more likely this day, a dry etch, some kind of a plasma etch or something to etch it away. And so we remove that silicon region. Notice that now what we've done is transferred the pattern from the photomask into the photoresist, from the photoresist into the wafer, into the silicon dioxide region. So the magic is we've transferred that pattern, whatever was on the mask, gets transferred into the silicon dioxide. Sort of. There's all kinds of optics issues as you try to push this to the limit. That's the basic idea. And this photoresist, remember, we said it's an organic layer. It's not going to handle high temperature processes and stuff. We don't want to melt or bake it on. So we actually remove it. We take the resist off, and now we have this patterned region, silicon dioxide pattern on the silicon layer that's whatever pattern was on the mask originally. Think of this as two-dimensional. We just drawn a little cross-section. Think of it as a big two-dimensional pattern. You can make lines, rectangles, all kinds of things, okay? We're halfway done. So this is our photolithography step. This is what we mean by photolithography or photo patterning. Now we take it, we have that, we're not done with the device yet, it's not really anything useful, but we do these things again. So now we do another step, you're already experts on this. We're going to, in this case, put in chemical impurities. We're going to fling some arsenic at this surface. The arsenic's going to get stuck in the silicon dioxide up here, but penetrate into the silicon wafer down here. So that's a matter of, now we're modifying the properties. We've changed it from something known as P-type material to something known as N-type material. But the key is we've now put in different kinds of chemical impurities to change the properties of that material. Remember, we used to get to change the properties by a lot. So we've now changed the properties there, right? I'm glossing over a lot of things, but that's the idea. So now we've got that layer. Now we need to finish out the device. So we deposit some metal. This could be, say, aluminum or something. We deposit it everywhere. We're going to now pattern it by doing another photolithography step. I'm not going to go through all the steps, but we put down another photoresist. We expose it with another mask, a different mask now. We get patterned regions in the photoresist, and now we're going to use those regions to etch through the metal. So again, we've transferred something from the photomask into the photoresist, into the underlying substrate, and now we have patterned metal. We have 3 different distinct regions, and those are going to be our source, drain, and gate regions in that final transistor. Okay? And you know, when you talk about, we said these are transistors, MOSFETs. We tend to refer to them as NMOS or PMOS, depending on whether this is N-type or P-type. CMOS just means we have both NMOS and PMOS. And the simple idea is we can have devices that turn on at positive voltages or devices that turn on at negative voltages. And that's really useful as we do circuits. Okay? So we do this. The silicon wafers nowadays are like 300 millimeters. We do it over the whole wafer at once. So now we're getting lots and lots of chips, lots and lots of devices on each chip. And it's a manufacturable process. Can you do all these things in massively parallel fashion? Within the wafer, we'll have chips. Each of these, a complete circuit on each yellow region is a chip. We call them a die or a chip, depending on how they're packaged. But now you have silicon chips that tend to be on the order of a few millimeters up to a couple centimeters in extent. We get a full working circuit on each one. Each one of these could be a full memory chip, a full microprocessor, cell phone chip, whatever. And notice on each wafer we get lots of chips, so we can now produce lots and lots of devices if you produce multiple wafers in a given fab. Okay. Yep. Yeah, I know. We got to roll. And we do this lots of times. I've oversimplified it, but we can produce lots of layers, lots of different layers of metal interconnect to make all these circuits we want to make. Okay, so I need to breeze through this, but let me just note that when we talk about a chip or a die, We mean one of those full working circuits within a wafer. It gets divided up into lots of die, which become chips once they're packaged. And we tend to package these things into things that you can put on a board. So the chip will go into a package that's got lots of leads on it, connect to a board. Each of these will be a chip. This looks like a memory module you might have plugged into your computer. So that's what we mean by chips and die and all that. So the last thing I want to cover, and I think is important, is Moore's law scaling. So Gordon Moore was at Fairchild Semiconductor and eventually went off and co-founded Intel. And he observed back in the 1960s that it looked like you were getting more components per circuit, and every year or two you were getting more and more devices per chip. That was Moore's law. So he actually observed this back in about 1966 when he said, look, this is log base 2 of the number of components per function, really the number of transistors per chip per year. And in case you're not good at reading log base 2, this was like 12 transistors on a chip, 100 transistors on a chip. So this is the very, very early days of integrated circuits, right? Not too far advanced from that transistor radio we talked about. And even back then, Gordon Moore said, well, it looks like every year or two, the number of transistors is doubling. So back in 1960s, he said, look, it's about doubling. And this was Moore's law. And it really wound up meaning the manufacturing cost. If you thought about year by year, the number of transistors per chip could go up economically. You could always try to build a hero chip that had a lot more, but you really couldn't get by with it. And the key is that that's been going on for a long, long time. This is a plot of Moore's law scaling since about 1970. So remember, Gordon Moore predicted it back here someplace. And look at what's happened in the 70s and the 80s and the 90s and the 2000s and the 2010s and all the way into the 2020s. That's been going on. So this is, still every generation, which is 2 or 3 years, the number of transistors on a chip doubles, but really the functionality of a chip doubles. And look at how far this has gone. It's gone from a few hundreds of transistors to tens of billions of transistors. And this is exponential scaling. Doubling every 2 years is exponential growth. So to have an industry that's been on exponential growth for 60 years is just remarkable. And this is what makes the industry so challenging and so remarkable. Okay? I do need to wrap up, but let me just point out that there's a lot of things that go into this you'll learn about this semester. But let me just show you one picture. If you want to really see in a nutshell why it's such a challenging industry, this is what's called a gate-all-around MOSFET. We went away from that simple planar structure. Now people are just on the cusp of making these structures that are stacked planes of silicon. This is a cross-sectional cut. This is actually from a research paper, but it's kind of where the industry is. This is the silicon region in the middle, this sort of oval block in the middle, wrapped by silicon dioxide, wrapped by metal. And you see this cross-hatching in here? Everybody see that cross-hatching? You know what that is? It's actually atoms. It's planes of atoms. If we're down at the point now where within the current device structures, you can actually count planes of atoms within the device structure. That's fairly phenomenal, right? I mean, 100 years ago, 120 years ago, people were still debating whether atoms even existed. And now we have an industry where you can actually count atomic planes within your minimum device structure. So not only do you do that, but notice they've made it so that they controlled the silicon thickness that was grown here to an exact number of planes. This dimension here is lithographically defined, so they've somehow figured out how to make this work way below the wavelength of light, or at least the wavelength of light as we think about it. And this is the one that's 5 nanometers thick. There's also one in the paper that's 1.5 nanometers thick, so you can really count the atomic planes in here. But that was a little hard to see, so I stuck with this one. So that's what the industry does. If you want a challenge, go home tonight, sit in your dorm room or something, try to figure out how you would make a device that you could actually count the atomic planes in. Okay, that's fairly phenomenal. Okay, so I don't want to talk much longer. We need to wrap up and get you on the road here. But let me just note that a lot of things are happening where we got to keep going, right? The industry can't slow down. Even though you're hitting these atomic dimensions are really pushing, AI is pushing us to go faster and faster and faster. So that's the pull. We got to keep going with that technology push. All right. So that's it. Thank you much. And enjoy the rest of your semester.